about our quantum numbers, and so now we're going to talk about that name of orbital column on the side of the summary values handout. Okay, so each atomic orbital has both a number and a letter. So the number corresponds to the principal energy level, which is the N column on our quantum numbers, and the letter corresponds to the secondary quantum number, which is the L column. Okay, and so the SPDF corresponds to a specific number in the L column. So this is back in your notes on page 6, but when L is equal to 0, that means that it's going to be an S. When L is equal to 1, that means it's going to be a P. When L is equal to 2, that will be a D. And when L is equal to 3, that will be an F. You don't technically need to write this down, but we are going to now use this information to go to our quantum numbers. And I don't have the numbers filled in because I can't do it. I can't actually write. But so the first orbital, there are 1 and 0, so that's going to be called 1s. Okay? And that's not what I wanted. Delete. Let's go here. 1s. Okay? Then the next orbital has a 2 and a 0. So this is a 1, and that's a 0, and that's a 1, and then a 0, right? So that makes 1s. Well, then when we have 2, 0, and the next 2, that makes it 2s, because the 0 corresponds to s for the letter. The next section, they have 2 and 1. And so when they have 2 and 1, all the way down, all 6 of those lines have 2 and 1. So that makes the orbital, the number is going to be a 2, but then the 1 for the L corresponds to P. Okay? And then moving down the page, our next section, it has 3 and 0. So that will make it 3s. Then after that section, we have 3, 1. So that makes it 3p. And just keep moving down, right? So then the next section, it's 3, 2. So a 2 this time corresponds to a D. So the next orbital is going to be called 3D. And then the last one, all the way down, it's 4, 0. So that makes it 4s. Okay, so those name of orbitals now we're going to use that with our arrows from up and down in the S spin quantum number section right here. And so that is going to allow us to do what's called orbital notation with electron configuration. So electron configuration tells us the ways that electrons are arranged around the nucleus. Okay, we call it electron configuration. That's a very broad term. It diagrams the electron structure of an atom by showing how the electrons are arranged around the nucleus in their energy levels and in their sublevels, so the shape that the electrons are traveling in. So we have three rules that govern the filling of these orbitals. Excuse me. The first rule is the Pauli exclusion principle. We already saw this, right? So no 2 electrons in a particular set of atoms can have the same exact set of 4 quantum numbers. That's why on our summary paper, every line was just a little bit different as we go. Okay, so to occupy the same orbital, 2 electrons must have opposite spin. So this we have right here, this is what we are going to be doing. This is what I call orbital notation. Okay, so you see how each line can hold 2 electrons, and one arrow has to be pointed up and one arrow has to be pointed down. And so that is one of the things, they have to have opposite spins. The other rule is Hund's rule. So when we're filling up our orbitals, we have to fill each section first. So we have to fill the 1s orbital before we can move on. We have to fill the 2s orbital before we can move on. The 2p is weird because it has 3 boxes or 3 lines, because p's can hold 6 electrons. And so when we do that, we have to think about it as being a teeter-totter. And so we have to fill the first arrow in all of them before we go back and fill the second arrow in all of them. And that's just to make it more even when you're filling in your orbital. So when we do orbital notation, it's important to know how do you, or how many electrons do you need to do. Because we said before, however many lines you have to fill for the quantum numbers, that's what you just do, right? Well, now you're going to have more spaces. So we have to know that the element is carbon for this example, so we know how many electrons to do. Well, carbon is number 6 on the periodic table, so its atomic number 6 tells us we're going to have 6 electrons. So that means that we're going to have 6 arrows when we're done, okay? And so when you fill in the arrows, remember they got to be up and down, but this is the one time that chemists are actually a little lazy, and instead of writing a full arrow, you can do a half arrow, and that's what I'm going to do. As long as you show the direction, that's what's most important. So we're going to start by filling in the 1s, whichever direction that you draw first in your arrows for the very first box. That's how the first arrow in each box has to be the whole entire time, okay? So I'm going to go up first in my 1s, so that's 1 arrow, 1 electron, 5 to go. So I need to put the second one in the 1s, pointing in the opposite direction. So that means the 1s orbital is filled, because it has 2, and it can only hold 2. So now we can move on to the 2s. So I put my third one up, because that's what I decided I'm going to put up first. And that is the third. Fourth is pointed downward. That is 4 electrons. We still need 2 more, but the 2s is now full because it has 2 arrows. So now we have to go to our 2p. And this 2p is where we have to do that teeter-totter balancing act, right? So I'm going to put number 5 in the first box, point it up because it's first in the box. But then the second one, I'm not going to put in the 2px to complete that box. I'm going to actually skip ahead and put it in the 2py. Notice how I also pointed it up because it's the first one in that box, and that's what you do. So we have 6 arrows, we have 6 electrons, we are done with the orbital notation. So the last question, how many unpaired electrons are found? So how many atoms, or how many electrons do not have a pair in their box? And that would be 2 electrons do not have pairs. Okay, so we're going to pause here and work on the backside of the summary for quantum numbers. There's electron configuration and orbital notation on that paper. We're going to do that in class right now, and then we will move on.